Okay, here we go. So
Why are you worried?
what do you do? This is a good model for other functions too. We deal with lots of piecewise functions in math and science because piecewise functions allow us to shift gears. Did I do the example like with, did we talk about like a parachutist at the beginning of the year in a piecewise function? I think that's just my Algebra 2 classes. This just seems like a good one. So if you want to model things like, let's say, the behavior of somebody who's jumping out of a plane, and you want to model their height as a function of time, what's that going to look like? What's going to happen there? They're going to jump out of the plane, and then there's going to be a period of time where they're in free fall, right? Okay? But then what happens? Well, actually, a couple things happen. They're in free fall for a period of time, and then they hit terminal velocity, right? And so there's a transition there, right? So we've already changed from one behavior to another behavior. They pull the ripcord, and things change dramatically, right? Then there's going to be a period of deceleration, right, where they slow down and they come to a new terminal velocity, right? Eventually they hit the ground and they stop moving. So there's a lot of different points in that model where we have to just completely, one function's not going to do the trick, is it? We're going to have to be able to shift and use multiple different functions depending on where you are in the descent to model that function. Well, that's normal. I mean, that's what we do. When we use math to model stuff, which is mainly why we use math, we got to be prepared to deal with that then with a piecewise function. And so let's look at an example. An absolute value function is very difficult to deal with as an absolute value function. It's difficult to do the calculus, but if we just turn this into a piecewise function, it's not so bad. Because if it's a piecewise function, it's a function that's defined differently for different parts of the domain, right? Think what that would look like on our table. There's just going to be a certain part of the table where it has a certain behavior and another part of the table where it has another behavior. No big deal, right? You just calculate the derivatives of each part in its own domain, right? Piecewise functions are really not that big a deal to do calculus with. You just do regular calculus with each piece of the piecewise function. Okay, but the first step is we got to write this as a piecewise function. So we have to remind ourselves, and this is the one I want to go back to several times throughout the year so you really get a good feel for this. What is the definition of, in terms of a piecewise function, of an absolute value function? So let's just make this really simple for a second, and let's just take something like the absolute value of A. How do I write that as a piecewise function? What are the things that could happen? Okay, so where A is positive, what's the absolute value equal to? A, right? So in the part of the domain where A is positive, it's just equal to A. Okay, what about the part of the domain where A is negative? It's negative A, it's the opposite of A. And then in between, where A is equal to 0, the absolute value of 0 is just 0, right? Okay, well this isn't an A, it's something. Or in this case, A is equal to a quadratic expression. And so we're going to set this up as a piecewise function then. Wherever this is positive, it's going to have, we're not going to have to multiply by -1. The function is itself. Wherever this expression for the values of x, where this expression is negative, we're going to have to make it positive by multiplying by -1. And wherever that expression equals 0, the absolute value equals 0, right? So what do you think our first step is going to be then?
Take the derivatives.
Well, we don't want to take we can't take the derivative yet because we don't have it written as a piecewise function. But in order for us to get this written as a piecewise function, what do we first need to know about this function? The domain. Okay, so in other words, where is it? I mean, it's defined everywhere, right? It's a polynomial. But what don't we know yet? Yeah, we don't know where it has these behaviors, do we? Where is this function positive value? Where is the function negative value, right? So wouldn't that be our first issue we got to deal with here? In order to write this as a piecewise function, which is our goal, we gotta know what are the domains where the function is positive and negative and zero, okay? So how might we do that? What do you think? What's your thinking on this? And we're just trying, okay, we could factor it, and there's no one way to do this, there's a couple ways we can do this. But we wanna know where all this stuff right here is positive valued and negative valued, okay? So if I wanna know where it's positive valued, let's ask the math gods where that happens. It's positive valued where it's greater than zero, right? So doesn't that just give us an inequality that we can solve? Okay? So x squared plus x minus 6 is greater than 0 where? So now we gotta come up with a strategy for finding out where. Now, one suggestion was factor it, and this one does factor it. What's it factor into?
Plus 3x.
X plus 3, x minus 2. Did you guys do anything like this last year?
Probably.
Yeah.
I don't remember the piecewise part.
Okay, maybe not, but you solved, I think you solved some inequalities like this,
Yeah.
right? And probably, if I'm guessing, did you guys do, well, I'm gonna quit talking, you talk, tell me what you would do here.
Well, the plot of Star Wars, you see, is
Get your money before the stock exchange.
There you go.
You can split it into two.
You could. I mean, I wanna know where the function is positive value. So one approach would just be, let's think of this in terms of maybe even just the graph of the function. Where are the zeros gonna be?
3 and 2.
Negative 3 and 2, right? So if I were gonna graph this thing, I know if that's negative 3 and that's 2, those are gonna be the zeros, right? And then all I'd have to do, how would I test to see if the function, where it's positive and where it's negative? Plug in test values. Like if I plug in 0, what do I get? Negative, don't I? Right? So the function is gonna be negative at 0, so it's negative on that interval. If I plug in something like 10, I'm gonna get positive times positive, right? So it's gonna be positive there. And if I plug in negative 10, I'm gonna get negative times negative, which is positive. So we would know that the function is doing something like that, right? Okay? Does that make sense?
yeah.
I mean, we could even look at this and say, you know, if these are, you know, we could get these signs just by looking at the signs of the factors, right? I know that if these are the zeros are at negative 3 and 2, in between I'm getting opposite signs, which makes it negative. To the left I'm getting same sign, so it's positive. To the right it's same sign, so it's positive. Okay? So just from looking at the behavior of this function, that helps us, right? We could set this up and we could say our domains are gonna be, what were they, negative 3 and positive 2 were the zeros?
Yes.
So when if x is less than negative 3, we had positive behavior, right? Okay. That was a place where the function was positive. If x was greater than
2.
2, in fact, I'm gonna give myself a little more room here. Greater than 2, it was positive, and in between it was negative, right? Okay? So when x is greater than negative 3 and less than 2, it was negative, and then the zeros would be when x equals negative 3 or x equals positive 2, right?
Could you write that as 1 though? Like, when x is equal to negative 3, comma 2, it's 0?
No, you don't want it. You don't want it because you want to write it so that the entire domain is represented in the piecewise function. Because you want to do it this way. Okay, is there another way? Let me see another way to do this That works. But I could take the same inequality. What was it, x squared plus x minus 6? Right, let's say we want to know where it's positive value. Okay. What if I were to complete the square? Okay, why might that be? And that's kind of I mean, I just want you to see why that might be a good strategy. If I complete the square, I end up with a single x on it. Right? What makes this a little bit difficult is the fact that I can't isolate x here, right? And it factored, so it was convenient, but what if it didn't factor? It wouldn't be so convenient, right? I mean, we still could do it that way. I could still find the zeros with the quadratic formula and then test the value of the function in between those zeros. And this strategy would still work, right? Okay. But what if I complete the square? I'm going to chase the 6 to the other side, so I get x squared plus x is greater than 6. What number would I have to add to both sides to complete the square?
Nine,
Well, I've got to add half of b
so
squared.
9.
So 1/4, right? Half of b is 1/2. Squared is 1/4. So if I add 1/4 to both sides, then what am I going to get? Well, over here, this is going to factor into x plus 1/2 squared, right? And the x plus half of b quantity squared. And that's going to be greater than, that's just going to be 25/4, right? 24/4 plus 1/4. Okay, now what? Square root. Okay, if I square root both sides, I'm going to get the absolute value of x plus 1/2, right? Remember, that's our true definition. If I square root something that's squared, I'm getting the absolute value of x plus 1/2 is greater than 5/2, right? Okay, and that's a pretty easy thing to write as an inequality, isn't it? Right? What's our rule if I have an absolute value inequality where I have an isolated absolute value that's greater than a number? It's good to review this stuff. What's the pattern there? If I have the absolute value of, call it capital X, is greater than A, then either what's inside capital X is
Greater than
A, or what's inside is
greater,
Less than.
less than negative A. It's extreme, isn't it? It's either big negative or big positive, right? So then what that tells us over here is that x plus 1/2 is either greater than 5/2 or x plus 1/2 is less than negative 5/2. Those are easy to solve. Just subtract 1/2, and I either get, where is this thing positive? It's going to be when x is greater than 2, or x is less than negative 3. Know what we got,
Yeah.
right? See my point? Okay. So that's a strategy that's always going to work, because we're always going to end up, when I complete the square, I'm always going to get a single x in there. I'm going to get an absolute value inequality that I can solve. Okay? All right. Just wanted you to see that. Okay, so now let's do this thing. So we got where it's positive, it's equal to just plain old this, right? So on this domain right here, it's going to be, our function is equal to itself. There and there. It's equal to its opposite where the function's negative, right? So here I'm just gonna change all the signs. Minus x squared minus x plus 6. And it's equal to 0 for the absolute value, where the function's equal to 0, right? So there's my piecewise function. Now I can just differentiate, right? And this actually ends up being a pretty easy problem from this point on. If I want to calculate y prime, what's the derivative of x squared plus x minus 6?
2x plus 1.
So it's 2x plus 1, where x is less than negative 3. It's negative 2x minus 1, where x is greater than negative 3 and less than 2. And it's 2x plus 1, where x is greater than 2. Okay? What about, here's a question for you. What about at negative 3 and positive 2? A lot of good stuff going on here. The analysis is kind of fun this way, because you can really have to think about this stuff. So what would have to happen for the derivative to exist there, at those two places? The derivative of 0 is 0, right? Okay, but what are the criteria for the existence of a derivative? Where does a derivative not exist? Say it again?
It's not
Okay, where the function's not continuous. That's true.
Sharp curves.
Wherever there's a sharp corner, yeah, right. So how would we know if there's, and this function, the function is continuous, isn't it? Right, we know it's just it's, if we, well, do we know it's continuous? It is continuous. It is continuous. And I can prove that, because if I take the limit of this function as I approach negative 3, what am I going to get? 0, right. If I take this limit of this function as I approach negative 3, I'm going to get 0, right? So I do know that the function is continuous, but how do I know that the derivative exists there? What would I have to do? This is really a high-level question. This is this is a really hard, like, high school concept.
Are you gonna?
A limit of what? Of the derivative, exactly. Yeah, we're going to take the limit of the derivative as we approach negative 3 from the right and the left, and we'll see if we get the same value, because that's what's going to indicate if we have a sharp corner, isn't it? If I take the limit of the derivative as I approach negative 3 from one side and I get a different answer than I do from the other side, doesn't that mean sharp corner? Right? The tangent lines would have different slopes, and so they'd be meeting at a sharp corner. So in order to test that, we would just take a quick limit here. The limit of 2x plus 1 as x approaches negative 3 from the left, right, from the negative side, is equal to what? Negative 1? Everybody agree?
Yeah.
Isn't it? Did I get that wrong?
Negative 1.
Oh, sorry, you're right, negative 5. Yeah, sorry. What am I doing? So negative 6 plus 1 is negative 5, okay? What's the limit as we approach of this function of negative 2x minus 1 as x approaches negative 3 from the right? Ah, it's 5, isn't it? Okay, so does the derivative exist there?
No.
No, we get a sharp corner, don't we? Right? So when x equals negative 3, it's undefined. Okay? We could do the same thing down here. What do you think is going to happen? It's going to be undefined. And how could you tell me that without even having to do any work?
Well, it's in, is it because it's an x squared, and so it has to.
I guess you could. I was thinking that was really tricky.
Wouldn't it be symmetrical?
It's symmetrical about what, though? It's not symmetrical about 0. I was thinking, that's good thinking. You were going to look for symmetry. but it's not symmetrical.
Well, wouldn't the absolute value make it symmetrical?
Mm-mm. No, it's not symmetrical, it's not symmetrical about zero. Right,
Oh,
and we can prove it, if we do a test for symmetry, I mean, you can prove this to yourself really quickly. This is f of x, right?
Yeah.
So what's f of negative x? F of negative x is gonna give us the absolute value of negative x squared minus x minus 6. Well, that's the same thing as x squared minus x minus, it's not the same thing, is it? Right, so you can see right away that it fails, it's neither odd nor even in this case. And we could have predicted that because look, I've got an x squared, I've got an x to the 0, and I've got an x to the 1, so we've got a mixture of the two, okay? Okay, so we'd have to do the limit, but we can do it real quickly. The limit of this function as we approach 2 from the left is going to be what? Negative 5? Yeah, right?
Yeah.
The limit of this function as we approach 2 from the right is going to equal 5. Yeah. Okay. All right, so then we end up with undefined at x equals 2. Okay, but from there on out, it's pretty easy. What's the second derivative going to look like?
2, -2, 2.
Yeah, right, so we just get 2, negative 2, 2 on our domains. And if we make a table out of this then, negative 3 of 2, right? Those were important places because those are the zeros of our function. Okay, now we need to know, are there any critical numbers? Right? So we'll go back to the previous page. Here's our derivative function. Okay, so talk to me about that. Do we get any critical numbers?
Negative. Or positive.
Okay, so
No, just negative.
the zero of this derivative is at where?
Negative.
Negative 1/2. Is that in our domain? No. So does this piece of the piecewise function have a critical number in its domain? No. How about this one?
That one does.
That one's at negative 1/2 also, isn't it?
Yeah.
And that is in its domain.
Yeah.
Okay, so we can fix that. So we get negative 1/2. What do you notice about negative 1/2 compared to this two? Yeah, halfway, isn't it?
So it's negative 1/2 here symmetrical.
There you go. So negative 1/2, we get a 0 for the first derivative. Okay. And then if we look down at this one, we get, once again, negative 1/2, which is not in its domain. So there's only one critical number in the whole thing, and it's right there. We know that the second derivative was positive, negative, positive in our three, right? Three parts, our piecewise function. So positive, negative, positive, right? And if I probably should pick a test point, so we'll go with negative 5, negative 1/2, 5, or something like that. So what is this guy then? What's the 0 mean for our first derivative?
It means,
No, the 0 of our first derivative always means horizontal tangent, good. And I have a negative concavity, so that's a maximum, right? And then every place over here, do these count as inflection points?
No.
No, they don't, do they? Right?
Because they don't exist, right?
Because
they're
they're,
undefined.
because there's no tangent line at those places, right? Because the first derivative doesn't exist. Right? Okay? And so we could graph this thing pretty easily then. What's it gonna look like? I've got so we know that the function was negative here, right? And if we wanted, we could easily plug that number in and get an ordered pair. I'm not gonna do that. But that's gonna be where we end up with our minimum. Well, actually, hold it's maximum.
It's
isn't it?
maximum and
Whoops,
it's
other way
positive.
around, so it'd be like this. Right?
Yeah.
And then what's this gonna be over here? If it's concave up and the function's continuous, doesn't it have to do that?
Yeah.
Mhm.
If it's concave up and the function is continuous, it has to do that, right? Okay.